Hello everyone, so this is problem number 61 of chapter Work and Energy from the book H.C. Verma. In this question it is given that a particle of mass m is kept on the top of a smooth sphere of radius r. So let this be a smooth sphere and the particle is kept at the top of the mass m. Is given a sharp impulse which imparts its horizontal speed v. Okay. Find a normal force between the sphere and the particle just after the impulse. Okay, so at this position, let me draw the FBD. What are the forces that is going to act here? First is gravitational force, that is m into g. Second force is normal reaction offered by the surface, that is n. And since it is performing a circular motion, so there will be net acceleration of v square by r in this direction. So we'll write that mg minus normal is equal to mv square by r. So normal at that location is mg minus mv square by r. So this is the normal offered by surface at top position. Part B, what should be the minimum value of v for which the particle does not slip on the sphere? Okay, so here it is asking that what should be the minimum value so that it will not slip. Okay, so it means it is losing the contact here. So to make it lose the contact, it means normal force is becoming 0. So from this equation, if normal is becoming 0, so the minimum speed which we need to impart is root under gr. If we just substitute normal as 0 in equation 1, we will get the velocity of root under gr. So if we impart a velocity more than root gr, so definitely it will lose the contact, it will fly over. Now part C, assuming that the v be the half of its minimum calculated in part. Okay, so now assume that the speed which we are imparting is root under gr by 2. Find the angle made by the radius through the particle with the vertical when it leaves the surface. So let this be center. When it is making an angle theta, let this be vertical, let this angle is making theta when it is losing the contact. So at this location, let the speed be u. Now how much height it has fallen. So if this is r, so this distance is going to be r cos theta. This full length is r, so this height through which this particle has fallen down is r minus r cos theta, that is r into 1 minus cos theta. Now what at this location, what are the forces that is going to act? First force is your mg force. Second force is normal reaction. And if it is moving with this u speed in this direction, so definitely it will have some kind of acceleration in this direction, that is tangential acceleration, and some kind of acceleration in this direction. This is centripetal acceleration, and this acceleration will be u square by r. So the component of mg along this, if this angle is theta, so this is going to be theta. The component of mg along radius is going to be mg into cos theta. So we'll write that net force towards its radius, that is mg into cos theta minus normal, is equal to mass into acceleration u square by r. So at this location it is losing the contact, it means normal is becoming 0 here. So u is going to be gr cos theta root under. So let me write that equation second, and we'll apply the loss in gravitational potential energy is equal to gain in kinetic energy. So initially it was, or we can write that total mechanical energy initially is equal to total mechanical energy finally. So initially it has a kinetic energy of half mv square. V is gr by 4, and initially it has a potential energy of mgr into 1 minus cos theta, if I am considering this as a reference level. Now final kinetic energy half m u square, that is u is equal to gr cos theta root square is gr cos theta, plus potential energy is becoming 0. Why? Because this block is coming on the reference level, so it is 0. So from here, if you calculate, you'll get a value of cos theta is equal to 3 by 4. It means theta is equal to, so this is the value of angle from the vertical which we are getting, where this normal is becoming 0. So we can write theta is equal to cos inverse 3 by 4.